Hello. So I'm going to talk about WebAssembly. This is a talk I gave back in January at NDC, which is why it's still got the NDC stuff on it. Who here heard about WebAssembly? Most of you, good. Who's actually used it in anger? Anybody? No, right, that's interesting. So I thought I'd just give a quick overview of what it is and why it might be useful. Oh no, we're back. Okay, so what is it? Well, WebAssembly this is from the WebAssembly website. It's a binary instruction format for a stack-based virtual machine. So what does that mean? Well, it's binary, so it's not source code. It's not JavaScript. It's like assembly language. It's stack-based, so it runs in a virtual machine. Which is stack-based. For those of you who've ever done any Forth, very similar idea to that. And it runs in a virtual machine inside the browser sandbox. The idea is to have a portable target for compilation of high-level languages, for example, C++, there's a Rust implementation, Kotlin, a few others, to make it size and load time efficient, to run it in a memory-safe and sandboxed environment, and also to support non-web embedding, so not just in the browser, but for other things like IoT and things like that. So why do this? We've got HTML, we've got JavaScript. Aren't they good enough? They've lasted us. They've done fine so far. Why do we need this? And the answer is performance. Interpreting JavaScript is slow. JavaScript frameworks are getting, like Angular and React, are getting bigger, so you've got bigger load times. You've got a lot of time and effort spent interpreting all that JavaScript on the fly. And some applications, things I'm interested in particular, audio synthesis, and also if you want to do advanced 3D graphics, you just haven't got the performance in an interpreted language to pull that stuff off. And also there are big non-JavaScript code bases out there which actually would benefit from being run in a browser. So doing something like this gives us a cross-compilation like this, gives us an opportunity to do some of that stuff. Now, haven't we surely we've tried things like this before? Yes, we have. We tried Flash, a never-ending security bonfire. You need a client installation. You're forever needing to update it. Java, again, you're always having to update clients. Microsoft gave us ActiveX in IE, but that was Internet Explorer only, which meant it was never widely adopted. Google tried a similar thing with something called Google Native Client. Has anybody used Google Native Client? Didn't think so. And then more recently, a thing called ASM.js. Has anyone heard of ASM.js? Yeah. So ASM.js was an attempt to build a subset of JavaScript that could be run efficiently, and that you could optimize ahead of time before running it and cross-compile from other languages. Pardon me. And actually, that's been taken up quite widely. But it's still quite expensive to parse, and it's still JavaScript, so you do still have a runtime environment for it. So what makes WebAssembly different? Well, it's an open specification, unlike Flash and some of the earlier things we were talking about. It's sponsored by the W3C. It's part of the browser. So all modern browsers now have WebAssembly as part of the implementation. It's adopted widely across all modern browsers. It builds on the existing ASM.js support that's there, which was also widely adopted. But because it's more like assembly language, it's a bytecode, it's faster to parse, and you can do some static and dynamic checks on it to make sure that it's actually safe at runtime. And I say promises near native performance. Because it's basically bytecode, you should be able to get fairly good performance out of this stuff. At the moment, it's still only promises. It's not actually, it's still quite slow. So the goals of the WebAssembly project were to build a portable binary format, to create a minimal viable product based on ASM.js and then add more features later, to have something that would execute within and integrate into existing web platforms, have some way of supporting it outside the web, and also to have two formats. So there's a bytecode format and there's a human readable format as well. So the idea is you can compile to the human readable format if you're debugging, but you can run the bytecode efficiently. So how does it work? Well, we have a compiler. There's a package called mscripton that will take C and C++ code and compile it down to WebAssembly bytecode. You then load the bytecode with a built-in JavaScript call, and then you call methods in that bytecode. At the moment, there's no integration with the DOM at all, which means that you can only run basically static functions. So there's a long way to go before it's universally applicable, but if you've got specific bits of processor-intensive code that you want to speed up in the browser, then this might be a solution for you. Just a quick, can everybody see that at the back? Is that big enough? If not, sorry. So this is a quick example of, so I've taken a very simple function to calculate a factorial of n, and shown how it compiles down to, so this is the bytecode that it gives us, and this is the human readable form of this. So this is all stack based. So get local says get the first item off the stack frame, which is our argument here, n, and push that onto the stack. Then take constant value of 0 and push that onto the stack. Then we do the equality operator, which says compare the two things on the top of the stack, and if they're the same, then we return 1. So that's that. Otherwise, take this first argument again and again, so push that twice onto the stack, and then put 1 onto the stack. Then we subtract 1, so that is our subtracting 1 here. So the top of our stack now has n-1 on it. Then we call ourselves recursively, so that's the factorial with that n-1. And then, so now on the top of the stack, we've still got this value, which is our original n, and the result of calling ourselves recursively, and we multiply the two together. So you can see it's all, there are no registers here, it's all stack based. And having it stack based makes doing some bits of the static analysis, I think, more straightforward, which is why they've done it that way. So a little bit of where we are with this. In March 2017, the community group announced that we've got browser consensus. That is, they've tested it on these browsers and it works to all the tests, or the majority of tests pass in Chrome, Edge, Firefox and WebKit. I'm guessing now that Edge is Chrome, that probably that's much the same. The current tooling we've got for this, so there's mscripton for C and C++ compilers. Kotlin has a direct compile to WebAssembly. Rust will, I think, uses mscripton in the back end, I think. The C# team have a project called Blazor, which actually uses, so this doesn't compile, this doesn't use mscripton. They have taken the core of the Mono project, compiled that to WebAssembly, which is about 2 meg. And so if you build a Blazor project, the first thing it does is upload basically Mono and then runs your C# code in that instance of Mono, which is an interesting approach. So it does make your initial page loads quite big because you've got 2 meg to load of the Mono, but that sits in your cache, so that only happens once, ever. And so generally it's fairly effective. And there's also, because I'm an F# fan, there's also a project called Bolero, which is using essentially the Blazor technology, but it uses F#. It's an F# compiler instead. There are some drawbacks to all this stuff. So because it's running in the browser, you don't have any control about the resources that you've got. You know, you don't know whether you've got a Core i7 or a Pentium or something running there, and the mono, as I say, this mono compiled runtime is quite big, and also because it's then running, you're essentially jitting .NET IL into WebAssembly, so there's obviously not quite as performant as going through C or C++ and using Inscription. So, should you use WebAssembly in your next web project? Initially I thought no, but now I think not yet. I guess unless you're doing something that is really quite CPU intensive and you want to do it all client side. So I'm just started dipping my toes into doing a bit of audio synthesis client side in this stuff, because again, it's all very computational. One of the problems is that you've still got to get everything. You've got to pass all your data into the WebAssembly sandbox and then back out again before you can. So there's a transfer cost as well. But if you badly need better performance, or you've got a big existing code base in an existing language like C or C++ that you want to run in the browser, then yeah, there are definite reasons. And as long as you don't need to interact with the DOM. So that's WebAssembly. As an F# fan, try Bolero. I think it's quite cool. It's like, if you've used Fable Elmish, it's like Fable Elmish, but even better. That's it. Any questions?
You said that you can't interact with the DOM, but the last one of these, there was a long talk on Blazor showing it doing kind of sort of MVC-like stuff and interacting with the DOM. Is it doing that by having a bit of JavaScript that it manages?
Essentially, yeah, you have to pass stuff into it, get the results, and then but the actual DOM interaction is done in JavaScript in the.
And that's being done for you.
Yeah. Yes. Essentially. Yeah. So you can't write code that talks directly to the DOM. You have to do your calculations, get that result, and then pass that into the DOM. Yeah. Anybody else?
Does it have direct access to like audio output?
No, you've really got, it is very, very much a closed sandbox for obvious security reasons. So you've got, you have access to essentially anything you've got in the browser, except for UI. Yeah.
You said that you wouldn't use it yet unless you wanted to do really computationally intensive stuff. What if you just really hate JavaScript?
Well, that too, yeah. Yes, that's another good reason. Yeah. Okay. Anyone else? No? Lovely. Thank you.